Chapter 9 is about the properties and attributes of functions. In this lesson, we'll talk about the three ways to represent information using a table, an equation, and a graph. Each have their strengths and weaknesses, and when put together, they tell a complete idea about the information. Remember, with constant differences, linear, quadratic, and cubic are all polynomial, and so their first, second, and third constant differences from the data help you decide what model to use, and a constant ratio will let you know that you're working with exponential data because it's repeated multiplication. In the opening example, we'll sketch a graph that we'll make up that will represent ticket sales being good, let's say at an amusement park, until a massive power outage happened on Saturday, and it wasn't repaired until late Sunday. So we will want the axes clearly labeled and also a title for the graph. My title is ticket sales. My dependent axis is going to be sales in thousands of dollars, and my independent axis is going to be days of the week: Friday, Saturday, Sunday, Monday. Ticket sales were good until a massive power outage happening on Saturday. So on Friday, let's say sales were about 7,000. And then it wasn't, like, maybe on Saturday it happened in the evening. So we had most of the sales from the Saturday, or maybe it happened like halfway through. So let's say we're a little bit above 4,000. And then it wasn't repaired until late on Sunday, but maybe some people came in afterward. Through social media, we advertised that we were open, so then let's say we got about $1,000, and then we were back to business on Monday. So this would be a graph that represents this situation. There could be several interpretations of it, but there are very clear pieces. You have your axes clearly labeled, and you have yourself a title, and this gives a quick visual that there was a dip in income because of the power outage, and then it went back up in sales after it was fixed. So the graph gives you a very quick, compelling graphic. In this example, we will make a table, an equation, and a graph to model the situation of Janet rowing across an 80-meter wide river at a rate of 3 meters per second. This graph and information will represent the distance that Janet has remaining before she reaches the other side, and we'll have to answer the question, when will she reach the shore? For my table for part A, I've clearly labeled my columns. My independent column is time in seconds, and then my dependent column is distance in meters. So at time 0 seconds, she has not gone any distance, so it's the initial amount of 80 meters wide. And then after 1 second rowing across the river, she's traversed 3 meters, so then she has 77 left. And then after 2 seconds, 74 meters left. As you can see, there's a constant first difference of -3 between the dependent values given equally spaced independent values. Therefore, the data is linear, and the first data point is the Y-intercept, and then the slope is going to be the constant rate of change. So we get an equation that her distance at time s in seconds will equal -3s plus 80. You could also write that as 80 as the starting amount, and then you're chipping away 3 meters per second. So presenting the function in that form tells the story a little bit better. Moving on to part C, I have my graph clearly labeled. My independent, which goes with the first column of the table, is going to be time in seconds. And then I have as the dependent axis the range values, the distance remaining in meters, and my title is clear. This is Janet rowing on a river. So we have these data points to plot. Or we could just think about the Y-intercept. So I have then on the y-axis here the data point 0, 80, and then 1, 77, etc. I don't want to have it too close to the y-axis, so I'm going to think about what would happen if I substitute in 6. So I substitute in 6 into S. I get 62. Plot that data point. It's a line, so I connect the dots. Now, I'm intentionally not finding out what the x-intercept is because in part D, I need to find out when she will reach the shore, and I want to show the strength of the function that we wrote in part B in determining that, because I want to emphasize here the strengths of each of the components of how you could represent information. To reach the shore, that's an x-intercept, or where d of s equals 0, so the dependent value, and that's the left-hand side of the function. And solving that yields that s in seconds is 26 2/3. That's how long it will take until Janet reaches the other side. In this example, we will start by creating a graph that will give us a visual to clue us into what function model we should use for this situation of a hotel manager, realizing that people will rent a room depending on the rent price. So the hotel makes money based on the price and the number of rooms that they rent, so they can't make the price too high because then fewer people will rent the room, and vice versa. They can't make it too low because even if they fill every room, they might not be maximizing their revenue. So I'll create a graph of this data. So the hotel manager did an experiment with $70 room rates. This was the revenue, and then moved it to $80. It increased the revenue, but as you can see, for each increase here in the room price, we're getting a smaller jump in the revenue. So that kind of feels quadratic to me, like a parabola that is reflected downward. So let's verify that with a graph. My axes are clearly labeled. Price per room is the thing that I'm changing. It's going to be the thing that I put into the system, the independent variable, and then the output is the revenue. And then I have a title that says something like hotel study. To make sure revenue is understood, know that it is equal to the price of the item times the quantity that you sell of that item. So this column here is actually the product of these two values. That's very important to recognize. Looking at the graph, we kind of see that it's arcing off here, and at some point we should have a maximum. So quadratics can be used to help you maximize or minimize a system. So I'll put this column into the calculator as L1 and this column into the calculator as L2 and run a quadratic regression model and check the R-squared value to see how well it fits the data. So I then do quad regress and make sure to store that in vars, y-vars, and then this is the regression model that the calculator gives me based on statistics using a least squared fit model, and then the R-squared value is equal to 1. I made sure that was turned on using diagnostic, and then I want to see these data points plotted with the regression model through them, so I do zoom 9. So I could do zoom stat, and I'll adjust my window accordingly to make sure that I have that arc of the parabola clearly on my screen. Now I would do calc 4, I do a left bound, I do a right bound, and then a guess, and then I read out the x coordinate that corresponds to the perfect price that I should charge to maximize my revenue. In the last example, we'll look at an investing. We buy a property at $100,000, and experts based on the market research that they've done, expect the property to increase by about 6% per year. And we could use a table, a graph, or an equation to predict the number of years it will take for the property to be worth more than $150,000. So we'll start off with a table, then we'll look at the graph, and then we'll come up with an equation to model. What I've done in the table after clearly labeling it is taken the initial value at time 0 of $100,000 and multiplied it by 1.06, which is the same as multiplying it by the equivalent of 6% and then adding that back on to the starting value. And then I took that value and multiplied it by 1.06, so forth and so on. So a spreadsheet would be excellent for this kind of information, and a spreadsheet would be like a table that would allow you to answer this question. But I'll just leave it with what I have here, and then looking at the table, the constant ratio is about 0.94, so therefore it's exponential. Notice it's 0.94 because I take the second value and divide it by the previous one to undo the multiplication that I repeated to get to each one. And after making a correction, because I'm taking the second one divided by the previous one, it's about 0.06. So let's take a look at how a graph can help us. So in the graph, it should look more exponential, but the way that I chose my spacing for the x and y axes isn't going to really show that exponential growth that we're getting from the repeated multiplication of 1.06. But here's the graph. I would have this all in the calculator, and what I would then try to do is find this intersection. From the table of data, I would come up with this equation where 100,000 is my principal or initial amount, and it's a percent increase, so it's 1 plus the percentage of increase as a decimal, 0.06, raised to the number of years that I'm having that increase, and then my target is my second y value of 150,000. So then I do second trace 5 for intersect, enter, 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 and then I find that the value of the property will increase to $150,000 after 7 years. So you could see that the table, the graph, and the equation all have their own ability to convey information given about a context.